All right, let me just go full screen. Okay, thanks for coming out. Just a reminder, if you took the course last semester and you wish to have a lab exemption, which means that you'll take your lab grades from the last semester and apply it to this semester, please send me an email notifying me that you want to do that with a snapshot of your grades. And then those grades from the last semester will be applied to this semester. All right? You have until the first lab happens, which is next Tuesday. So if you want to have an exemption, then you better let me know before the first lab that happens, which is next Tuesday, okay? Okay, so last class we covered brief signals and systems review and started a little bit of theory about communication systems. Now we're going to wrap that up this hour. And then after that, the next couple of hours will be dedicated tutorial questions to get you, so you have enough knowledge and everyone's at the right, I guess, stage of the game so that you can do the pre-lab for the first lab if you decide to, if you're actually doing the labs. Okay? So we talked about channels. You want to transmit signals through channels, and the objective is to take a look at the output signal, and you want to make sure that the input matches the output as it passes through the channel. Okay? Hi guys, I'm talking now. Thanks. Okay, so you have some signal x of t, which is your message signal, which is converted into an electrical signal through the transducer, and you pass it through what's known as a linear and time invariant system. All right, so this is a linear and time invariant system. Linear and time invariant system. Okay, so that's an important property if you want to make sure that the thing works. So, and then the output would be the received signal or the received message. All right. So we usually characterize a channel or whatever system you're trying to put the system or the signal through with an impulse response, which is called h of t. And then you also take a look at it in terms of the Fourier transform, which is h of s. And then this here means that you want to take the Fourier transform. Okay? So you can either take a look, and if you want to take a look at the output, you can either convolve the two signals together. So you have x, you have the signal x, and then you have the impulse response h. You can either convolve them together, or what you can do is you can take the Fourier transforms of them both, multiply them together, and take the inverse. So that's a very common property that you learned in 532. All right? So here's a very fundamental linear time invariant system property. So if you remember the stuff from ELE 302 and all the stuff that you learned from the first year, if you put in a signal with some frequency, a sinusoid with some frequency, okay, the output of the LTI system should be another sinusoid that has the same frequency, but the amplitude might change, and you might experience a little bit of a phase shift at the end too. Right? So the input is a sinusoid at some frequency f naught, okay, and the output is a sinusoid of the same frequency, but there might be a different amplitude and a little bit of a phase shift that's associated with the actual signal. So what I mean by that is you have some signal like this, right? So it's characterized by f of naught. This is the frequency. Okay, if you put it through some system, we'll call it S. The output may give you some delay, right? So we'll call this, I guess, T naught. But the frequency is the same. Okay. If this amplitude is A, then the output amplitude might be something different. It might be A prime, for example. So there might be a different output, like a different amplitude in terms of the output, and there might be a little bit of phase shift at the end as well. So that's a characteristic with linear time invariant systems. So that's something that is very well known. Okay. So okay, I pretty much drew that. So you have some input, it's coming in, so with some impulse response that's characteristic of that channel, you see what the output is. All right. So here's one thing that you may or may not know. So supposing that x of t was a complex exponential, right? So you can realize a complex signal with certain electronics, but you have some complex exponential, right? The output is going to be another complex exponential of the same frequency. So notice that this and this are pretty much the same. The complex exponentials are the same, but there's going to be a different amplitude, right? So there's going to be a different amplitude at f0, okay? And then there's going to be a phase shift as well. So ARG stands for the argument, which is the phase of a complex number. So this is, there's going to be a phase shift as well. Right? So when you put the signal in, the output's going to be it's going to be a signal of the same, so there's going to be so same frequency. So as the outputs is going to be the same frequency, but you might have a different amplitude, and the phase shift there might be a little bit of a phase shift. Okay? So that's what we have here. So different amplitude, and then you're adding an additional phase on top of what we have here. Okay, another consequence. So let's say you put in, so that was just the general case with the complex exponential, and then you have a sinusoid. We have some amplitude, right? And then we have some frequency associated with the sinusoid. So this is the frequency. And then you have some phase shift. So let's say there was a phase shift already. If you put this through your system, what's going to happen is that you'll have, so you'll see that the amplitude, this stays the same, because it's linear, but then you'll see that there's an additional amplitude that's applied on top of the actual signal. So there's a different amplitude now. Okay. Notice that the frequencies are also the same. So here and here, same frequencies. Okay, same frequencies. Also, we have the same phase shift as well. Sorry. What the heck? Oh, sorry. Sorry, my bad. Sorry, I should probably turn off this keyboard. I put my palm on it and it went haywire, so okay, good. All right, so the same frequency, and then notice that there's the same phase shift here, sorry. The same phase shift is between here and here, but there's an additional phase shift. So it's pretty much the same, it's a consequence of what I've been talking about before. Okay, so you put in a sinusoid of some frequency, the output might change the amplitude slightly, and there might be an additional phase shift on top of your signal that's already there. So it's just, something that is well known. Okay, here's one last consequence. So this was the, you can represent a periodic signal in terms of its Fourier series, right? So this would be the Fourier series of a periodic signal. Fourier series representation of a periodic signal. Okay, so you can represent this as a weight of, a sum of complex exponentials, all right? So then the output, what will happen is that, remember, with the impulse response, it's a linear time invariant system, which means that if you put in a bunch of individual signals into the system, the output, you just take each one of those, apply the actual system output, and then you just add them all together, which is what's happening here. So notice that you have the same weighting here, right, d of n, but then there's an additional amplitude, so additional amplitudes, I guess. All right. Okay, so additional amplitudes. So you you have some frequency that is, or some amplitude that is applied on top of each each frequency component. So notice that when you're doing the Fourier series component, you have sinusoids of multiples of the fundamental frequency. So what you're doing here is you're doing pretty much the same thing, but then you take multiples of the fundamental frequency and see what the amplitude is for the actual channel, and then you just apply it like that. So notice that the complex exponential stays the same, right? It's the same frequency. Okay, and then there's an additional phase shift. This is just a consequence of the same thing, but. So you don't have to remember the math about this. You just remember that when you put in a signal that a signal that's a sinusoid of some frequency, if you put it through your system, the output may change the amplitude slightly, and you might get additional phase shift on top of that as well. So it's a very common property for LTI systems. Okay. All right, and last but not least, this is what we talked about before. You put in a signal x of t, right? And then what you get for the output is you can just multiply the Fourier transforms of them both, right? So if you put it through, h of f, sorry. So you have this box here, okay? The output is just, well, you multiply these two things together, right? X. Okay, and then if you want to find the inverse, you just take the inverse Fourier transform. So remember, when you're convolving in time, you perform multiplication of frequency. So that's actually what's happening when you're putting in a signal into a system. You're actually performing convolution with the input and the impulse response. Okay, so performing convolution with the impulse response to get y. Okay, all right. Okay, there we go. Okay, so just a little tidbit of how you would measure the frequency response if you actually didn't know what the actual function looked like. Okay, so if you remember, there was I believe there was a lab test that you did for ELE 202 where you took in sinusoids, you took different frequencies, and you actually measured the magnitude and phase, and then you figured out what configuration the circuit was, whether it was an RC series, RC parallel, and so on and so forth. So what you do here is if you want to figure out what the frequency response of your system looks like, if you don't have it in front of you, if you wanted to actually measure it on your own, you put in a sinusoid of some frequency, which we'll call F1. Okay, you put it through your system, and then you observe what the amplitude is and also what the phase shift would be. So put in, a sinusoid of frequency F1. Okay, so this is the first step, and then the second step would be examine amplitude. Okay, so then you do that. All right. So then, once you figure that out, if you want to figure out what the magnitude is, it's very simple. So at frequency F1, right, what you do is you usually, if you want to figure out what the magnitude is, you usually find the ratio or the gain. So what you do is if you set this as an amplitude of A, you see what the resulting amplitude is of B, and then you just divide by B over A. And that's what the resulting amplitude would be. So if you want to figure out what the magnitude is at this frequency, you just figure out what the amplitude is here, right? And then you divide it by whatever amplitude you set at the beginning. By convention, usually we set A is equal to 1, because that way you don't have to worry about the division, so you just take a look at the output and that's what you use. Okay, so usually A is equal to 1 to make things easier, all right? Therefore, the magnitude would just be B, okay? So then what you do is when you decide to plot this, you see what, you figure out what frequency you set it at, and then you just plot what the magnitude is. So that's the first frequency. Then you do it again for another frequency. So let's try it for F2 now. So F2 is another frequency where it's larger than the first one that you set. So what you're doing is you have a dial for your function generator, and you keep increasing the frequency. Increase the frequency, take a look at what the magnitude is, increase the frequency again, take a look at what the magnitude is, then you keep doing that until you kind of see that there's no output, or the magnitude is quite small. And then you just plot all those points together and you're good to go. Okay? So this is the second one. You take a look at what the magnitude is, right? And then you just find B over A again. Okay? And then you plot it here. And then as you start increasing the frequency, you notice that this one is going to be bigger than both of the other ones. And then you'll start to see that as you start increasing the frequency, usually for baseband systems or usually for some channels, the magnitude will decrease as you start increasing the frequency, which actually makes sense. So as you start increasing the frequency here, you'll notice that the amplitude is actually quite small, and that's where it maps to over here. Okay, so as you start increasing, and then you get to a point where the gain starts to decrease, and then you can keep going until you see that the output's negligible, and then you stop. Okay. Okay. So that's pretty much about LTI systems. The reason why I want to talk about that is I wanted to talk about this particular idea, which is called a distortionless transmission system. So what I mean by distortionless is that if you have your signal and you want to transmit it over the channel, you want to be able to recover it, and you want to be able to see what the original output signal was with very little noise or very little modifications to it, so you can see what the original signal looked like. So you ideally want to have a system where the channel doesn't have any distortion, or it doesn't modify the signal as much, so you can actually recover the signal quite accurately. Okay, so a distortionless system means that if you put your signal in through the channel, the output should satisfy this constraint. Okay, so what I mean by distortionless is that if x of t goes through the channel, the recovered signal should satisfy this equation here. Okay? So you put in a message signal, the output should just, so it'll just take each point and multiply by some factor, some system gain, and then it'll take every point and shift it by some constant delay, T naught. Okay? So what I mean by this is that if you have some signal like this, let's call this x of t, I guess, all right? You put it through your system, the output y of t will perhaps make it a little larger, I suppose, and then let me just move this over. Yeah, good. Let's do that. Okay, so the output might look something bigger like that. Oops, sorry. Let's move over here. right? And then it's delayed by some constant T naught. Okay, so that's the definition of a distortionless system. So you put some signal into your channel, the output should take every single point and multiply by some gain factor. It could be larger, it could be smaller, doesn't matter. And you have to make sure that every single point is delayed by the same amount. All right, so that's what we classify as a distortionless system. So what does this look like in frequency domain? So we have this signal, so this actually makes sense to us, all right? If you want to take a look at what it looks like in terms of the frequency domain, all you have to do is, well, we had some signal like this, and then when you put it through your system like that, right, the output should be this guy, right? So that's in time domain. We want to take a look at it in terms of frequency domain because when you're doing the Fourier transform and all that, it gives us a little more insight on what's actually going on. So if I decide to take a look at this in terms of the frequency domain, right? Remember, what's going to happen is that I need to perform multiplication, right? So I have to multiply these two things in order to get what the response looks like. Or you want to convolve this in time domain, right? So this is in time here, and then this guy here is in frequency. Okay, so that's what we want to take a look at. So you just multiply the two together, that's fine. Okay, so we're going to take the Fourier transform of the output here, right? So whatever output comes in, this is the output that we get. So we want to take a look at what this Fourier transform is, which is what we're doing over here. When you take the Fourier transform of a constant, you can just bring that out, okay? And then this is what we get, all right? And if you remember the property for the Fourier transform of time shift, right? So if I had some signal x of t minus t naught, if you take the Fourier transform, you just get the same Fourier transform without the time shift, and then you multiply by e to the minus j2 pi f t naught. Okay, so this is the time shift property. Okay, that's a property, and then this pretty much comes here. That's where that comes from. Okay, so this is y of f. Sorry. Okay, I want to figure out what my impulse response is. Well, I already know that. So I know that y of f equals h and then x. Okay, so I just have to divide by x, bring this over here, right, to get my impulse responses, and that's what I get. So if I bring this guy down here, that's my final equation. So this is what it would look like in frequency domain. So what this is saying here is that for all frequencies for the channel, it should multiply each frequency component by some constant k, and it should do it for every single frequency value that you have. Also, there's going to be a linear phase shift by 2 pi t naught. So there's going to be a slope of negative 2 pi t naught for the phase. So this is what it looks like. Okay, so what does it look like pictorially, what I just talked about? So remember, you can represent a complex number, you can represent the Fourier transform in terms of its magnitude component, right, and its phase. Okay, so in this case, this thing over here would be the phase, right, if you ignore the j, so there's a minus, and then there's a 2 pi f t naught, right? So this would be the phase. So this would be, so this is minus 2 pi f t naught, that's the phase, and this is the magnitude here. So it's just k. So for all frequencies, you want to scale the frequency components so that they're by a factor of k, and then there's a, so remember, when you're plotting the phase, remember the frequency is the independent variable. So what's happening here is that you have a slope of minus 2 pi t naught. So if you want to have a distortionless system, in ideal case, you want to make sure that the magnitude is just flat, so you're multiplying each frequency component by some factor k, and then the slope, or the phase, is linear. Okay, so the phase is linear. Okay, so that would be the two criteria for a distortionless transmission system. All right? Any questions so far? Okay, just let me know. Okay, so there's a big problem. Usually in a lot of real communication systems, especially those that are seen in practice, it is actually not possible to have a system that will be able to multiply all frequency components from minus infinity to infinity by the same constant factor. the electronics are non-ideal, so it's actually not possible for you to achieve this. And so it's not possible to have this condition here. So this is due to, the electronics and non-ideal situations and so on. Situations and etc. Okay, so it's actually not possible to actually do this. Ideally, it would be nice, but usually there is no such possible configuration that can actually do this for us. So what do you actually do in this case? How can we actually make it so that we can achieve distortionless transmission, but in a non-ideal scenario? How would we actually do that? Well, what you're going to have to do is you're going to have to relax your constraints a little bit. Instead of making it go from -infinity to infinity, you want to make it so that it is satisfying the distortionless transmission criteria within a certain range of frequencies instead. So instead of doing it for the entire range of your frequencies, just concentrate on a particular band of frequencies and apply that criteria instead. Okay, so that is something that is more realistic that you actually want to do instead. Okay, so in this case, a realizable, what you want to do is you want to do it so that it satisfies the distortionless property over some specific frequency range from FL to FU, where FL is the lower limit and U would be upper. Okay, so in this case, instead of having it completely flat all across the spectrum, you only have it flat within a certain range of frequencies, which is what we have here. Okay, so and what's happening here is that this dashed line here is the ideal case. Okay, this is the ideal case. And what's happening in the dark black lines are what you would want to expect if you're just expecting it within a certain frequency range. So what's happening here is that in between, so this is -FU and -FL, right? In between this range, you expect the slope or the phase to be linear. So here is linear, and we don't expect it to be anything outside. And then if this is FL and this is FU, right, we want this to be linear as well. So within a certain specific frequency band, you want the distortionless property to be applied, and then you don't really care about anything else. All right? Okay, so in many cases, even if you want to get exactly the distortionless case, it's actually still not realizable as well. So you want to be able, even though you're confining it within a certain range, even though it's a little more realizable, it actually is not, unfortunately, with all the electronics that are around. Okay, so what you're going to do instead is that what you'll do is you're going to apply the distortionless criteria, but within some tolerance instead. So instead of making it, the frequency spectrum flat, between a certain frequency band and the slope is linear, what you'll want to do instead is you want to make sure that the magnitude only drops by a certain amount between the actual frequency bands instead. So instead of it being a constant flat spectrum, you want to make sure that it only drops by a certain amount, which is a little more realizable. Okay, so you consider systems that satisfy requirements within specified constraints. So what I mean by this is that instead of the spectrum being constant between a certain range, okay, allow some tolerance. And that's a little more realizable too. Okay, so spectrum, sorry. Okay, some tolerance instead. Okay. So here's a quick example. So this is actually a realizable low pass filter actually. So if you remember from electronics, if you have an RC filter, you can consider this as a low pass filter, where any frequencies that are bigger than a certain amount, you set them to 0. Okay. So if you wanted to find the frequency response, all you have to do is figure out. So you turn this into frequency domain. This is in time domain. So you turn this into frequency domain, right? And if you want to figure out, what you have to do is you want to figure out what the transfer function is. You want to figure out the output over the input. If you want to figure this out, it's very easy. Remember, all you have to do is, I will show it, but all you have to do is just do voltage division, right? So all you have to do is figure out what this voltage is here. If you want to bring this into frequency domain, you know that the impedance here is 1 over j omega c, right? And then the impedance here is just R. So if you want to figure out what the voltage would be, right, all you have to do is just do, the voltage. No. So what you do here is you figure, so let me just call this ZR. Let me just call this ZC. So if you want to figure out what the voltage is across here, you just do voltage divider, right? So you do ZC divided by ZR plus ZC, and then multiply by VI, and that'll be your V out, right? And then you just do V over VI, and that's when you solve that. So when you do this and you solve this, you'll get this guy over here. I won't I won't show that for you because this is not a 302 course. I just wanted to show you an example of what it would be. You know, there are systems that can actually approximate distortionless transmission, and an RC filter is one of them. Okay, so when you do this, when you actually find, when you find the actual transfer function and you want to take a look at what the output is, this is what you get. All right. Now, if you want to figure out, so what we usually do here is, if this is our, our transfer function, so to speak, you want to figure out what the magnitude and phase are. Well, that's very simple. You just find the magnitude and phase of this. And if you want, let me see here. Let me just go down. Let me make some room here. Sorry, where am I? Here. So if you wanted to figure out how to do this, it's very simple. All you have to do is, if you know that the magnitude of some number squared is equal to the number itself, and then if you multiply it by the conjugate, you'll get the magnitude squared. And then all you have to do is just take the square root. Okay, and then you can get that. Okay, with the phase is very easy. What you can do is you can split this up. So what you can do is you can take so if you want to take the phase of this, okay, what you do is you take the phase of the numerator, subtract the phase of the denominator. All right, so what's going to happen here is that you'll have phase of 1 subtract phase of 1 plus j 2 pi FRC. Okay, so when you do that, you will get this. Just want to show you that. So this is what the magnitude will look like, and this is what the phase will look like. Okay. All right. So now we have those. So this is an RC, this is an RC filter. All right. So what we want to do now is this: when you're passing, signals through this actual channel, so you can consider this as a channel. It's actually not strictly band limited. So as you start increasing the frequency, you'll see that it kind of tapers off, and it doesn't exactly go towards 0. So if you want to figure out what the bandwidth is, if you want to figure out what the bandwidth of this channel is, you can figure out what the 3 dB bandwidth is. All right. So how do you figure out what the 3 dB bandwidth is? It's very simple. All you have to do is figure out what frequency you need to make sure that you drop the power by half. Okay. So if the 3 dB bandwidth is defined as f of 0, what you want to do is you want to make sure that the power, in this case, you just take the magnitude squared of the Fourier transform that gives you your power. So this squared would be the power, I guess, so to speak. Okay. All you have to do is figure out at what frequency you'd need to make sure that you drop the power. So usually you take the DC component, square that and divide it by 2. So you want to figure out what this frequency is. All right. So if I substitute, so remember h of RC was this. So if I substitute f of 0 into here, right, and I square it, I will get this guy, right? So let me just write this out. So you have h of RC. It was 1 over. Okay. So I need to square this. So square this. Okay. And then I have to substitute f of 0. So f of 0 goes here. So when I do that, I get this guy over here. And then usually with RC filters right at 0, you should get the spectrum, you should get the power equaling to 1. So, or half power. So that's what we have here. So you equal it to that. And then when you solve this, all you have to do is just, take the inverse of both sides. When you finally solve for this guy, you'll get that. Okay, I'm not going to show you how to do that, but actually, yeah, sure, what the heck. So if you wanted to solve for this, sorry. Okay, so if you wanted to solve for this, just take the inverse of both sides. So you get 1 plus 2 pi f0 RC squared equals 2, right? Because you're flipping, you're doing the inverse. And then you can subtract by 1 on both sides, right? And then what you'll get is 2 pi f0 RC squared equals 1. You take the square root, and then you rearrange, and that's what you get. Okay, so I just wanted to show you that. It's pretty straightforward. Okay, so this is what is known as the 3 dB bandwidth frequency. So this would be the point where at a certain frequency that you put into the system, once you pass that point, the power of the system will drop by half, and then you can consider that to be the bandwidth of your system. All right? Okay, so once we figure out this, so using FO, so we know that this is the cutoff frequency, okay? So, or not the cutoff, the 3 dB bandwidth. So what I can do here is I can take the inverse, I can re-express this so that it's 1 over f naught equals 2 pi RC, okay? So what I can do here is you can see that there's a 2 pi RC term for both the magnitude and phase. So if I replace this with 1 over f0, what'll happen is I get this result now. So the 2 pi's and the RC's here, right? They become 1 over F0, which replaces that. Okay, so you can represent this in terms, you can represent the magnitude in terms of the 3 dB bandwidth. So if you wanted to achieve some, performance, if you have some 3 dB bandwidth parameter that you're using to determine the rest of the components or using it to assess performance, you can use this transfer function with respect to the 3 dB bandwidth so that you can, get the desired magnitude and phase that you want. So notice that, this is, F0, so 1 over F0 is 2 pi RC. And then I just replace each of those guys with 1 over F0, and that's what you get. All right? Okay, so this is what it would look like in terms of the magnitude and phase. So this is just a rough sketch. So right at F of 0, you'll notice that the amplitude drops to 1 over square root 2. That's the definition of half power, right? So if I substituted F of 0 into here, right, what will happen is that will cancel, so you get 1 over square root 1 plus 1, right? And you just get 1 over root 2, and that's what happens here. Okay, so at this particular magnitude, or this particular frequency, your spectrum, it drops by 1 over square root 2. Okay, also interestingly enough, if you put in F0 here, you'll get minus tan inverse of 1, which is actually 45 degrees, or minus pi over 4. Okay, so that's why you have a minus pi over 4 here, because of F of 0. And then right at F of 0 here, and then actually no, that's fine. So F of 0 is pi over 4, then as you let the frequency approach infinity, then it makes sense that the angle would approach minus pi over 2. So this is a pretty good, it's a pretty good result here. Okay, so if you probably noticed by now that this low-pass, this RC system actually doesn't represent a distortionless system. Remember that between a certain range of frequencies, you want the magnitude to be constant. But within the DC frequency to, I guess, the 3 dB bandwidth, in between there, the magnitude is not constant. So magnitude is not constant here. Okay, that's not good. Also, the phase is not constant too. Like the phase is not linear, so the phase is not linear. When the phase is not linear, that means that the slope is not a constant. Okay, so when something is linear, that means that the phase, or the derivative or the phase is actually constant. All right, sorry. Okay. So what do you do in this case? So what you'll have to do is you'll have to relax your constraints a little bit. You'll want to make it so that it might be. You want to make sure that you minimize the distortion such that it drops only by a certain amount in between a range of frequencies. So it doesn't have to be linear per se. You just want to make sure that it just drops instead of it being constant. So you have to relax your constraints a little bit. Okay. So what we'll do here is I'm going to do a little example. All right. So let's consider a system where we want to make it so that it sort of satisfies the distortionless transmission case, but with specified constraints, which means that it's not going to be quite constant in between the two bands, but it may drop by a little bit, and that's okay. All right. So we're only going to take a look at the magnitude response. We're not going to take a look at the phase for now, anyway. So just take a look at the magnitude response, and what we want to do here is we want to make sure that if you want to satisfy the distortionless transmission, you want to make sure that from 0 to 10 kilohertz, the magnitude drops by no more than 10%. Okay? So what I mean here is that if h of f is some gain, we'll call this a, all right? H of 0. Okay? If I substitute h of 10 hertz, this can't drop by more than 10%, which means that it can only go down to 90% of what it was before. So 0.9a. So I want to make sure that this is what we're looking for. So what I mean by it does, the transmission is no more deviation than 10%. You want to make sure that it doesn't drop by more than 0.9 of whatever value you see at the 0 frequency. Okay? So that's what we have here. So right at 10 kilohertz, all right, we want to make sure that the magnitude drops a point. So in this case, we have a magnitude of 1. We want to make sure that it doesn't drop by more than 0.9. Okay? So we have to figure out exactly how to design this RC system so that we will achieve this particular result. Okay, So what we mean by here is that in between this range, so from 0 to 10 kilohertz, we'll make it so that it's approximately constant. So that's what we mean by, there's a maximum deviation. So it's approximately constant, and the phase is also approximately linear as well. So how exactly do we do this? How do we actually figure this out? So what you need to do here is you have to figure out the right 3 dB bandwidth. So you have to figure out find the right 3 dB bandwidth. So how exactly do you find the right 3 dB bandwidth? Well, it's characterized by the resistor, the resistance and the capacitance of the RC system. So we have to find R and C to define correct 3 dB bandwidth. Okay, so that's what we need to do. So we have to figure out the right components in the RC system so that it'll give you the desired deviation at 10 kilohertz. It's within 10% of a tolerance with the actual maximum. Okay, so how exactly do we do that? Well, here's a couple of things that you want to take a look at. You notice that with an RC, this is a low-pass filter, so it's an RC circuit, so that you'll notice that as you start increasing the frequencies, you'll notice that it monotonically decreases, which means that it'll decrease over time as you, not over time, but it'll decrease as you start increasing the number of increasing the frequencies in your system, right? Also, the maximum amplitude is found at the DC component, which is equal to 1, all right? Which actually makes sense, because if you have your transfer function like this, it was 1 over square root 1 plus, 2 pi f, not 2 pi f, but f over f naught squared, okay? At f of 0, you do get a magnitude of 1. Okay, which makes sense because f0 is actually not 0, f0, not at 0, sorry. At 0 hertz, right, you'll get the magnitude to be 1, right? Because that goes away, then you just get 1 over 1, and there you go. Okay? All right. So what we need to do first is we have to figure out what the 3 dB bandwidth is, and then ultimately we have to figure out what the constant is for that. So that's very simple. So we're going to call the, let's see here. So we're going to call this value f of 1. Okay? So f of 1 is equal to 10 kilohertz. Okay? So we know that at 10 kilohertz, we want to make sure that the magnitude is at 0.9. So remember, the transfer function for the RC system was 1 over plus and then f0 squared. Okay? So we want to make sure that when this guy is 10 kilohertz, okay, we want to make sure that the drop is 0.9. Okay? So that's what's happening. So the drop here, so at 10 kilohertz, the amplitude, or the magnitude is 0.9. And that's what's happening here. So we want to solve for f of 0 such that it gives us a magnitude of 0.9 right at 10 kilohertz. Okay? So when you finally solve this, so once you figure this out, okay, so once you figure out what f0 is, so solve for f of 0, and then once you finally solve for that, you plug it into here, and then you can solve for R of C, and you get that number. So this, because you have a product of, R and C, so this actually, you can have multiple different values to satisfy this constraint. So you can have a resistance that's very high, and then you can have a capacitance that's very low in order to satisfy this, or you can have a very high capacitance, which is actually impractical, and then you can have a low resistance, which will actually give you that much. Okay, so this is what we need in order to satisfy the 3 dB bandwidth, and also the fact that when you substitute in 10 kilohertz, you get a drop of 0.1, which is 0.9 in terms of magnitude. Okay, so now that we have that, let's see what's going on here. Just want to double check. Okay, so now that we have this, okay, so what we need to do now is we've only figured out, let's see here, we figured out what the 3 dB bandwidth is. So 3 dB bandwidth is solved. Okay, so what we want to do now is let's just take a look at the phase. Now consider the phase response, okay, just for now. Okay, so what's going to happen here is that at the desired frequency 10 kilohertz, where our magnitude drops by 0.9, but then let's also take a look at the phase as well. So at the phase here, we remember that the phase for this system is equal to minus tan inverse 2 pi FRC. Okay, So at this particular frequency, right, so you substitute F1 into here, we will get some phase associated at this particular frequency. So what we can do here is we could kind of approximate what the linear phase would be if you want. So we can do that, and then the reason why we're going to do this is going to be apparent much later. But let's approximate what the linear phase will look like. So at this particular point, this is 0, okay? And here, you'd substitute f of 1 into your phase, right? So this here would be h of RC, 10 kilohertz, right? 10K. Okay, so when you substitute this into here, so I want to find the slope. Right? How do you find the slope? It's usually rise over run. So you take this point in terms of the y, so you want to find this point here. So this difference would denote this, and then this is the frequency of F1, this is 0, which is this guy over here. So you want to find the slope, and when you do that, when you substitute 10K into this and you find the arctan, you get minus 0.451. And we know that 10 kilohertz is 10 to the power 4, right? So this is 10,000 or 10 to the power 4. And then the slope is roughly minus 0.451 times 10 to the minus 4. So why are we actually doing this? Why do we actually want to figure out what the phase is? Well, this will actually tell us what time delay we need in order to satisfy a distortionless system. Remember that when you want to have a distortionless system, not only do you consider the magnitude to be constant, or in this case within some tolerance, you also want to make sure that there is a constant phase shift for every single value that's in your signal. And you want to figure out what that is by taking a look at the phase. Okay, so now that we have this, all right, remember that the slope was equal to minus 2 pi t naught, and we figured out what the slope was already. So if you want to solve for what this delay is, you get 7.2 microseconds. So this means that for a distortionless transmission, okay, this means that the 3 dB bandwidth is equal to whatever it is, right? So so we solved that already. For distortionless transmission, the delay is T naught equals 7.2 microseconds. So that's the desired delay that you need in order to achieve distortionless transmission with the desired 3 dB bandwidth. Okay? All right. So I've got a couple more slides here, and then we'll take a break. But the RC low-pass system has a certain frequency response. If you want to approximate it in terms of distortionless transmission within 0 to 10 kilohertz, you have to make it such that the time delay is going to be 7.2 microseconds, right? And you want to make sure that this fluctuates between 0.9 and 1, so it doesn't drop by anything lower than 0.9. Okay, so that's what this is saying here. So your time delay is 7.2 microseconds, and this will have to vary between 0.9 and 1 if you want to make sure that it approximates distortionless transmission. Okay? All right, so I'll go through this really quickly. I don't want to bore you with this, but this is an example of a bandpass system. So what we talked about earlier was a baseband system where you're taking a look at frequencies from 0 up to some frequency that is off 0. So when we're taking a look at bandpass, you're considering a range of frequencies that are not at the origin anymore. They're offset from the center. All right. So when you consider this would be a bandpass system. I won't bore you with the details, but sorry.
Can you repeat what you said about baseband?
You don't remember what baseband was?
Yeah, but can you just repeat the region?
Okay, baseband means that the frequencies range from 0 up to some point. It's centered at 0. Bandpass is away from the origin, right? So if you want baseband, it looks something like that. Okay. Right, so this is B of X, and then bandpass looks something like that. Okay, and this is FL and then FU. Okay, FU and then FL. Okay, does that make sense? Okay, so we're taking a look at a bandpass signal. I won't bore you with the details here, but what you can do is if you wanted to solve for this, what you'd have to do is you'd have to find the parallel impedance. Okay, so this here would be J omega L, and this here would be 1 over J omega C. Okay, so if you wanted to figure out what the voltage would be at this point, so VO over VI is equal to 1 over J omega C parallel with J omega L, right, divided by plus R, right? And then you'd solve for that. So that's what you get. If you simplify that, if you get this, then you will get this guy here. Well, then that's in terms of S, okay? So when you substitute J omega into here, right, so when you, actually no, sorry. We will put that into here. When you simplify this, what you'll get is this expression over here. Okay? There's a lot of different things that are going on. So this constant Q is what is known as a quality factor. And I'll talk about the quality factor in a little bit. And then this here f of 0, it's what's called the resonant frequency. So what the resonant frequency means in this case, if you remember from 302, is that your system no longer has an imaginary component. So the system is actually purely real, which means that there is no phase shift. So it's at the point where the magnitude is at its maximum, there's no phase shift, and that's whatever magnitude you get is the highest one possible. So it's called the resonant frequency. Okay? So the reason why the quality factor is so important is because it defines the bandwidth of your bandpass signal. Okay, so this quality factor. So I won't derive this in detail, and I just want to show you an example of a bandpass system. But if you wanted, so this is your bandpass. If you wanted to figure out where the 3 dB cutoff is, so this here is your 3 dB between these both. This would be the lower end, and this would be the upper end. So the reason why the quality factor is so important is because it actually defines how much bandwidth your system will have, right? So the larger the quality factor, the higher the bandwidth is going to be, okay? Similarly, the smaller the quality factor you have, the smaller the bandwidth you're going to have, okay? So when you increase the quality factor, the system, what is known as, becomes a little more selective. So what selective means is that you can design electronics so that it can accommodate for the bandwidth of the system a little better. Okay, so usually circuits have a quality factor between 10 and 100. So with this, the 3 dB bandwidth, what it does is that the center frequency, which we'll call f of 0, right? So it's actually called the resonant frequency too. But the 3 dB bandwidth is defined between 1 and 10% of whatever this value was. So 1 and 10%. So what they're saying here is that the separation or the range between where the f of 0 would be, the 3 dB bandwidth is plus minus 10% or plus minus 5%. It depends on what you choose, but that's usually what that would be. Okay? All right. So a couple of more definitions and I'll take a break. So we have what's known as a narrowband signal. So what I mean by narrowband signal is that you have a bandpass system, but the difference, or the bandwidth, is actually very small. Okay, so the bandwidth is very small compared to its center frequency. So what I mean by this is that if you have your center frequency, let's say it's at maybe 10,000 hertz or 100 kilohertz, for example, the bandwidth in between plus minus 100 kilohertz is very small. It might be plus minus 50. So the center frequency here is much larger than the bandwidth that is plus minus at this point. Okay, so the bandwidth is small compared to. So what I mean by this is that the frequency of where the band centered is much, much larger than the bandwidth itself. Okay, so there's a performance measure we have here, which is called the fractional bandwidth. Okay, so what the fractional bandwidth is that it just measures, how much of a ratio you have between your bandwidth of the actual signal with the actual frequency itself. So the smaller the number is, the smaller your bandwidth is with respect to your center frequency. So it just gives you a little bit of a performance measure. Okay, so when you want to design distortionless bandpass systems, it can be very challenging because either you have, in this case, this is what we've seen before, right? So actually, no, sorry, this is the case that we have here, where it's actually very small, or it can be the case where it's very large. It's actually happened in the past. So usually the bandwidth can be bigger than the actual frequency itself, but it's very rare. But usually this is the situation we look at. All right. So usually what people do is they try to restrict this ratio so that it lies between 0.01 and 0.10, or 1 to 10%, as we talked about before. Okay. So here's some examples of taking a look at practical communication systems for long wave and short wave radio. When you want to take a look at transmitting signal, the channel is usually your frequency is at 100 kilohertz or 5 megahertz, depending on what radio you look at, and the bandwidth is actually quite small. It's either 2 or 100 kilohertz. And then you have very high frequency, or VHF. The carrier frequency is 100 megahertz, and the bandwidth is 2. So you can see that the carrier frequency is very large, but the bandwidth itself is very small. And the reason why you want to do narrowband is, we'll get into that much later, is you want to be able to transmit as many signals as you can within the same channel. So that's why having signals that are narrowband is important, because the smaller the signals are, the bandwidth, the more signals you can fit into the channel at the same time. And we'll talk about that later when we get into frequency division multiplexing for amplitude modulation. But usually the smaller the bandwidth, the more signals you can cram into the actual channel, and you can actually receive more signals. And you just put a filter on the signal that you want to listen to. Okay, and then you have microwave and optical, which is actually going to the larger range. But I just wanted to show you some examples of distortionless systems where you have, the center frequency and the bandwidth as well. Okay, so, all right. So I'll tell you what. We'll take a break here. I'll come back and then I'll talk about this briefly, and then we'll start your tutorial for the rest of the class. Okay, thanks.